If you got this equipment at home, try it out. All you need are some ice cubes, a container, a hot plate, and a thermometer. Drop the ice cubes into the plate, measure the temperature. Turn on your heating element and just set it and forget it. On the other hand, with the thermometer, every 30 seconds, measure the temperature. What's your hypothesis of what the outcome would be? Obviously, the temperature will go up, but how will it go up? Will it go up linearly? Will it go up quadratically? Will it go up square rootly? What could it be? Or maybe it's something weird. Well, turns out I had a student in the past do this experiment, and this is the collected data they received. Starting off with an ice cube, you'll notice the temperature more or less remains the same. And if you've been paying attention to what's been happening in the experiment, you'll notice it isn't until all the ice is melted that the temperature will finally start to rise. And it'll rise up at a rather predictable rate, almost as if there was a linear correlation right here. Mind you, the student wasn't super careful, so there might be quite a few outliers. However, interestingly, after you've reached a certain maximum temperature, it begins to flatline for quite some time. In fact, if you're super careful with your experiment and started off with really cold ice cubes, let's say at negative 100 degrees Celsius, then you'll probably have a graph that looks something like this. The moment you add heat to the ice cube, yes, it begins to heat up quite rapidly, until you reach the threshold of 0 degrees Celsius. At that point, the temperature stabilizes and locks in for a couple of minutes. Eventually, when all the ice has melted, the temperature then rises again at a predictable rate, until you reach the next threshold, which is 100 degrees Celsius. And as long as you have lots and lots of liquid in there, it'll take quite a bit of time before the temperature will finally increase. However, once all the water has boiled away and now you have water vapor, now you can heat up the water vapor to above 100 degrees Celsius. And this is a quite realistic diagram of what it is to heat up water. All right, where the temperature will just go up gradually and then it'll flatline. And it'll flatline for much longer than it took for you to increase the temperature of the water itself. So what's happening at these 2 points over here? Well, scientists borrowed a Latin term called latere, which means to lay hidden, and that's what we call it here. We call it latent heat or hidden heat. What's really going on? Well, it takes a lot of energy to break bonds. So starting off with a solid, to convert a solid into a liquid, you need to break those bonds first. And even more intense is to break these liquid bonds into bouncing off each other gaseous bonds. And that's why it takes a significant amount of energy to do that. If you don't believe me on this, well, how about we just do a very quick experiment? I'll start off with a balloon and a lighter. Ready for this? Ready, steady. Woo-hoo-hoo! Well, I'll try it again, but this time around with a balloon filled up with water. Let's do it again. Ready, steady. Nothing happens. You can try this one at home. Isn't that neat? Now, if you look over here, that's not the balloon burning. That's just the soot, because this is a hydrocarbon combustion. All right. So as long as there's water in here, it's not going to increase the temperature of the system beyond 100 degrees Celsius. In this case over here, the water is probably around 25 degrees Celsius. So I need to keep that heated up for quite some time before this will even reach boiling temperature. And even if it has reached the boiling temperature, I have to evaporate all of the water first before it'll go above 100 degrees Celsius. So this rubber remains rather safe. Now you know. Well, another thing that hopefully you know is that energy cannot be created or destroyed. So in other words, if we want this to happen in reverse, it's just going to be a mirror image of the same exact picture. So for example, if you have steam and you want to condense the steam and eventually convert it back into ice, it's pretty much this picture over here, but drawn completely backwards. And I do want to emphasize a very important point over here. I don't know if you guys have ever burnt your fingers before with steam, but there's a very good reason why. All right, steam is normally at a very high temperature, so in order for it to drop down to the same temperature as your hand, which is around 35 to 37 degrees Celsius, it needs to drop bucket loads of energy before it can do so. And that's why steam can be used to sterilize things. All right, because it has to release a lot of thermal energy before it reaches the same temperature as your body itself. Maybe this is a good time to talk about the second law of thermodynamics, which simply states that if you have a hot object and a cold object, and you pour them all together into the same container, you're going to get nothing more than just lukewarm water. And it's going to be nearly impossible for that lukewarm water to separate on its own back into hot and cold again. You have to put an effort to separate it. So that's effectively what's happening when you get burns. All right. And also, there's a very good reason why we use steam to sterilize things, because it's going to dump tons and tons of energy before the substance finally, the steam becomes the same temperature as the substance. So how would we calculate out latent heat then? Well, it is a measurable value. And usually when we measure it by how much energy it takes to completely transform it from one state to the next. And there are two states of conversion, either from solid to liquid, or from liquid to gas, or vice versa, gas to liquid, liquid to solid. And the number will be the same, except the sign will be different. And that's why in the formula itself, we just write down a plus minus. You as a human being have to figure out when should you use the plus sign and when should you use the minus sign. As for the formula we covered the last day, Q is equal to mc delta T, we don't need to worry about it. It's self-correcting, and that's because of this delta T over here. If our final temperature is greater than our initial temperature, then our Q will be greater than 0. In other words, heat is added. And if our final temperature is lower than initial temperature, well, the only way for that to happen is if you take heat away, or heat is removed. And that's what you have to do with regards to these equations over here. You have to choose when to use a plus or a minus. If you're heating up a substance, then use a plus sign. And if you are trying to cool it down, like throwing it into a refrigerator or a freezer, then you have to make sure there's a minus sign in order for the math to work out. I don't expect you to memorize any of these numbers over here. They're all available on a lookup table, but it is your responsibility to know where to look for this information. For example, if you're trying to melt ice, where should you look? That's right, latent heat of fusion. Meanwhile, if you're trying to vaporize the substance, hopefully you'll know that that's a latent heat of fusion. Sorry, right over here. Yeah, fusion to freeze, vaporization to vaporize or to boil away. And that's how I remember how to use this lookup table over here. Another important aspect of this lookup table is that different objects have different melting, freezing temperatures, same as boiling. And that's how we're able to actually take a liquid and actually separate it out. There's a method called distillation, and what you're doing is you're trying to bring an object up to a certain particular temperature, and you know that at that specific temperature, that's when that substance will start to evaporate, and then you can collect those vapors afterwards. How we do some math problems now. How much energy is needed to boil off 2 kilograms of water that started off at 24 degrees Celsius? There's two things you got to factor in here. First off, it takes energy to raise the temperature of the water from ambient room temperature up to boiling temperature. Next, if you want to completely boil it off, you then have to stay here for quite some period of time. So the total thermal energy needed in this situation over here is the amount of thermal energy to heat it up from 24 up to 100 degrees Celsius, plus the amount of Q needed to vaporize it. As for what the numbers should be, well, I'll give you all of that. It's all available on lookup tables. So let's say in this example over here, I've gone through the effort of looking on the lookup table, and here are my givens. And you're trying to look for the total thermal energy. Some textbooks use QT, others listed it as ET. It's up to you which one you use. I'm going to give you guys a moment to try solving this yourself. Did you guys get to the answer? I hope you guys got to this answer. 5.2 million joules. Some textbooks will write this down as 5.2 megajoules. It's bucket loads of energy. And as for the intermediate numbers, hopefully you got these numbers here. So this is an insane amount of energy over here. And that's what I was emphasizing from before. It takes a lot of energy to heat up the water itself. And that's why often water is an excellent heat sink. Maybe you've heard of this back in junior grades. where water is able to maintain the thermal temperature of the Earth itself because it takes so much energy to heat it up. And once it's heated up, it's going to give away a lot of thermal energy before it can finally cool itself down. It's the very reason why you don't want to go swimming in May or June, early June, in a big lake, simply because it's still cold from the wintertime. It'll take a while before it heats up. And even late into September, even though the temperatures may have dropped, or at least the air temperatures have dropped, the water is still swimmable because it's going to take a while before that lake water is able to lose all of its thermal energy. One common mistake I see with students is that when they're trying to solve these problems, let's say that you're trying to melt ice from, I don't know, negative 20 degrees Celsius to 40 degrees Celsius. Many students will just draw a single straight line and hope that it'll work out just fine. So they'll just use one formula. However, you only get 1 out of the 4 marks. If you're trying to melt ice and bring it up to room temperature or whatnot, keep in mind that the ice is going to go through many states. First off, you have to bring up the melting ice up till the melting temperature of 0 degrees Celsius. Then you have to melt the ice with the latent heat of fusion. Lastly, with that really cold water you got, you bring that temperature up to the temperature you desire at the end. So there's many states involved when you're trying to heat things up. And it gets even more complicated if you want to take that ice and bring it up to steam. Now you have to go through yet another latent heat, but this time around of vaporization, plus another mc delta T. And if you've been paying attention to the value of C, it does change depending upon whether it's ice, water, or water vapor. So you can't just be combining them together because the slopes are different. They're not the same. Well, how about one more practice question for you guys to work through? How much thermal energy is needed to heat up 1 kilogram of ice at negative 10 degrees Celsius to water vapor at 120 degrees Celsius? Give you guys a chance to try this out. Ready for the reveal? All right, here we go now. Hopefully you guys had all the values pulled out from the data charts. Another thing to keep in mind is that you're looking for a delta T, a change in temperature. So you first have to find out the delta from negative 10 degrees Celsius all the way up to 0, or finally finishing off at 0, starting off at negative 10. So it's a gain of 10 Celsius degrees. Then from 0 to 100 degrees Celsius, well, 100 subtract 0 gives you a delta of plus 100 Celsius degrees. Lastly, up here, please don't sub in 120. That won't work out. You're looking for a delta. So from 100 all the way up to 120 is what you need to sub in there. And yep, it's a lot of effort to calculate it out, but I hope the results are that. All right. And yes, it's an insane amount of energy. As a reminder, 1 joule of effort is taking this and raising it up 20 centimeters, about the size of the bottle itself. Try lifting up 3 million times. That's how much energy is needed to melt ice. Tons of energy. For more adventures like this, go ahead, have some fun with your homework. If you're still sticking around, let's quickly solve them together right now. Brandy is made by distilling ethyl alcohol, which is done by boiling the alcohol until it turns to gas. And let's say I give you the latent heat of vaporization for it. How much thermal energy is required to distill 0.75 kilograms of ethanol? Q is equal to mLV, but are you going to use plus or minus? Good. You're boiling it, so it must be plus. That's something you have to keep in mind. All right, when should you use a plus sign and when should you use a minus sign? I hope 8 is fairly straightforward. As for 9, you have to go through a few steps. In fact, drawing a heating curve might help you out. Block of ice starts off at negative 15 degrees Celsius, then you heat it up, and it turns into this ice water slurry. In fact, something I forgot to mention before is how do you calculate out a thermometer? It's actually fairly straightforward. Have a container filled up with nothing more than ice and water. Let it stabilize for a few minutes, and as long as you have an ice water slurry, it's guaranteed to be at 0 degrees Celsius because you have both states of ice and water all at once. That's why the value remains the same. You got to break the bonds of all the ice that's in the container before the temperature finally elevates. So once all of the ice has melted and turned into water, then the temperature will gradually increase until it reaches 100 degrees Celsius. It's going to hang around here for quite some period of time. And that's why when you take a look at your latent heat of vaporization, it's a crazy huge number. It's something like 3.5 times 10 to the 6. I've got to cheat now. 2.3 times 10 to the 6. All right, 2 million joules per kilogram just to convert from boiling water into steam. Then it'll finally increase up to 115 degrees Celsius. So it is a lot of calculations involved in solving this one. How much heat must be removed by a freezer in order to change 20 60 kilogram sections of water from 0 degrees Celsius into ice at 0 degrees Celsius? Hopefully you've experienced this before. All right, you want to make ice as fast as you can. So you put the water into the fridge, you close the freezer, half an hour you open it again and you look at it and then you go, holy cow, it's still water. You close it, leave it for another half an hour, you open it again, maybe you'll see a thin sheet of ice on top. You close it again afterwards, and it isn't until you fall asleep and wake up a few hours later that when you open up the freezer that finally the ice has melted. It takes a ton of energy to drop down water and freeze into ice, and then after that, then it'll drop below 0 degrees Celsius. All right, it takes tons of energy to be removed, and that's what I want to point out. When you're trying to remove energy, how must you deal with the formula? That's right. This formula is not self-correcting. You need to plug in the minus sign into the formula as a human yourself, because you know that that's what needs to be done. And yeah, it's going to take tons of energy to remove it. All right, 60 grams times 20 will give you 1,200 grams. Convert it to kilograms because that's what's needed for this formula here. Of course, if you're learning this in chemistry class, often they'll measure it in joules per kilogram. So watch out for that. Units have to work out. Number 11, a tank containing lots of water cools down and completely freezes. Now, if you want to do the opposite, how many hours must you keep the heater on to melt and bring it back up to 15 degrees Celsius again? Because that's what you want to do. Maybe it's soup. Water soup. Okay, so let's figure out how much thermal energy is removed from this. And yes, it's a two-stage process. Q is equal to mc delta T for the amount of thermal energy needed to bring it down to 0 degrees Celsius, and then you'll have to take out even more thermal energy for it to freeze, and that involves your MLF. And remember, you're removing. This one you have to put a minus sign. The first one you don't have to, because this will be self-correcting. Remember, your final temperature will be at 0 degrees Celsius, and it started off at 15 degrees Celsius. So the minus sign would have automatically been factored into the formula itself. So this is how much thermal energy is required to be removed to cool down 740 kilograms of water, which is, you know, a small little swimming pool for kids. All right, it takes a lot of energy. So it's going to take a ton of energy to heat it back up again to bring it up to a freezing 15 degrees Celsius for you to go diving in. So how long will it take? Well, we're going to use that same number again. And from the last unit, when we talked about mechanical energy, well, the formula hasn't changed. Power, by definition, is work over time. So how much work is needed to heat up the equivalent of 2.9 times 10 to the 8 joules of energy? That's equal to power times time. So then time will be equal to work divided by power. Sub the values in, rearrange super carefully, and you'll see that it'll take quite some time. Sweating is important. That's what cools your body. And you'll notice that on a very humid day, the sweat does you no good. It's muggy, it's painful. You just want to stay inside a house with air conditioning, as many of you probably are right now. So in order for sweat to do its job, you need to make sure that the outside is nice and dry, or hope that it's nice and dry outside. Because even if it's 30 degrees outside, as long as you have dry air, you feel perfectly fine. It takes a lot of energy to take away, to convert an object from liquid into gas. So when you sweat, All the water's intent is to take away the thermal energy from your body so they can finally break its bonds and turn into water vapor. Remember, energy cannot be created or destroyed. It must be taken from something else. So as long as the air is rather dry, the water has a tendency to want to turn itself into a vapor, and in doing so, it takes thermal energy away from you. There's another way to prove this demonstration. Just take a cloth, dip it in room temperature water, then swing it around for a couple of seconds. If you feel the cloth on your face again, you'll notice it feels cooler on a dry day. Try doing the same experiment on a humid day. You slap on your face, and you'll realize that the cloth is at room temperature. Nothing special about that. Okay, so let's answer question number 12, now that you understand. So to cool the body, the jogger has to sweat. So how many grams of water needs to be evaporated in order for this jogger to be more comfortable? Let's go and do the math for this. So this is an isolated system. The amount of thermal energy that is used to heat up the sweat is equivalent to the change in temperature of the jogger, him or herself. And you're trying to figure out how many kilograms of sweat is needed to be evaporated. So you take this formula and you isolate for M sweat, sub in all the givens that are listed over here, and you'll find out that you'll need about a Tetra Pak's worth of sweat to cool a jogger down. Something interesting to note out over here is that you might have thought about it, well, isn't the heat capacity of water at 4,200 joules? And some of you might say, well, humans aren't made purely out of water, and that's partially true. But I also wanted to emphasize another thing. This amount of thermal energy required to evaporate does change. All right. If I pour water on top of a table, the water will naturally evaporate on its own. You don't need to boil it. So you can see that the amount of energy demand for it to evaporate will actually be a lot less. I guess one last thing before we end off. I wish I had the equipment over here, but you can boil water at room temperature. It's quite insane. All right, I'm not talking about adding heat to the water. All you really need to do is to prevent something from crushing the water so that's in its current state right now. We've got about 300 kilometers of air squishing down on us right now. So if we remove all that air pressure, water, interestingly enough, doesn't really want to stick with itself at 24 degrees Celsius. In fact, it wants to be a vapor. So if you attach this to a pump, a vacuum pump, and you remove all the gas that's inside this container, the water will immediately start to boil. Boiling is a conversion from liquid into gas. Wish I had that equipment here with me. Maybe you'll find a YouTube video that will share with you those cool experiences. That's about all I have to share with you right now. Catch you in the next episode, and do your homework.